Hello everyone, this is Srijit and welcome to MCAC35 Advanced Database Management Systems. Today, we continue with transaction processing in distributed database systems. Let's see the alternative models of transaction processing. For many applications, the blocking problem of two-phase commit is not acceptable. The problem here is the notion of a single transaction that works across multiple sites. For example, transaction closing an organization boundary. No organization would like to permit an externally initiated transaction to block local transactions for an indeterminate period. Alternative models carry out transactions by sending messages. Here, code to handle messages must be carefully designed to ensure atomicity and durability properties for updates. Isolation cannot be guaranteed in that intermediate states are visible, but code must ensure no inconsistent states in result due to concurrency. We can use persistent messaging to avoid the problem of distributed commit. Persistent messages are messages that are guaranteed to be delivered to the recipient exactly once, neither less nor more, regardless of failures. If the transaction sending the message commits and are guaranteed not to be delivered if the transaction aborts. Database recovery techniques are used to implement persistent messaging on top of normal network channels. To understand persistent messaging, consider how one might transfer funds between two different banks, each with its own computer. One approach is to have a transaction span the two sides and use two-phase commit to ensure atomicity. However, the transaction may have to update the total bank balance, and blocking could have a serious impact on all other transactions at each bank, since almost all transactions at the bank would update the total bank balance. In contrast, consider how funds transfer by a bank check occurs. The bank first deducts the amount of the check from the available balance and prints out a check. The check is then physically transferred to the other bank where it is deposited. After verifying the check, the bank increases the local balance by the amount of the check. The check constitutes a message sent between the two banks so that funds are not lost or incorrectly increased. The check must not be lost and must not be duplicated and deposited more than once. When the bank computers are connected by a network, persistent messages provide the same service as the check. Two-phase commit will have the potential to block updates on the accounts involved in funds transfer. So we have an alternative solution to debit money from source account and send a message to the other side, and the side receives message and credits destination account. Messaging has long been used to distribute the transactions even before the computers were invented. There is this issue of atomicity. Once transaction sending a message is committed, message must guaranteed to be delivered. Guarantee as long as destination site is up and reachable. Code to handle undeliverable messages must also be available. For example, credit money back to source account. If sending transaction aborts, message must not be sent. Error conditions with persistent messaging. Error handling is more complicated with persistent messaging than with the two-phase commit. Code to handle messages has to take care of a variety of failures situations, even assuming guaranteed message delivery. For example, if destination account does not exist, failure message must be sent back to source site. When failure message is received from destination site or destination site itself does not exist, money must be deposited back in source account. The problem also exists if source account has been closed. So we need get manual help to take care of the problem. There are many applications where the benefit of eliminating blocking is well worth the extra effort to implement systems that use persistent messages. In fact, few organizations would agree to support two-phase commit for transactions originating outside the organizations, since failure could result in blocking of access to local data. Persistent messaging therefore plays an important role in carrying out transactions that cross organizational boundaries. Workflows provide a general model of transaction processing involving multiple sites and possibly human processing of certain steps. For instance, When a bank receives a loan application, there are many steps it must take, including contacting external credit checking agencies before approving or rejecting a loan application. The steps together form a workflow. So in workflow, there will be human intervention processing of certain steps. Now let's see the implementation of persistent messaging. Persistent messaging can be implemented on top of an unreliable messaging infrastructure, which may lose messages or deliver them multiple times by these protocols. First one, the sending side protocol. When a transaction wishes to send a persistent message, it writes a record containing the message on a special relation messages to send. The message is given a unique message identifier. The message delivery process monitors the relation, and when a new message is found, it sends the message to its destination, and the message delivery process deletes a message from the relation only after it receives an acknowledgement from the destination side. If it receives no acknowledgement from the destination side, after some time it sends the message again, and it repeats this until an acknowledgement is received. If after some period of time that the message is undeliverable, exception handling code provided by the application is invoked to deal with the failure. Writing the message to a relation and processing it only after the transaction commits ensures that the message will be delivered if and only if the transaction commits. Now let's see the receiving side protocol. When a site receives a persistent message, it runs a transaction that adds the message to the received message relation, and provided that the message identifier is not already present in the relation. After the transaction commits, or if the message was already present in the relation, the receiving side sends an acknowledgement back to the sending side. Note that sending the acknowledgement before the transaction commits is not safe, since a system failure may then result in loss of the message. In many messaging systems, it is possible for messages to get delayed arbitrarily, although such delays are very unlikely. Each message is given a timestamp, and if the timestamp of received message is older than some cutoff, the message is discarded. All messages recorded in the received messages relation that are older than the cutoff time can be deleted. Next, let's see concurrency control in distributed databases. We show here how some of the concurrency control schemes studied earlier in DBMS can be modified such that they can be used in a distributed environment. We assume that each site participates in the execution of a commit protocol to ensure global transaction atomicity. The protocols we describe in this section require updates to be done on all replicas of the data item. If any site containing a replica of the data item has failed, updates to the data item cannot be processed. Let's first see single lock manager approach. The various locking protocols studied earlier can be used in a distributed environment. The only changes that need to be incorporated is in the way the lock manager deals with the replicated data, and we shall assume the existence of a shared and exclusive lock modes. Let's first see single lock manager approach. In the single lock manager approach, the system maintains a single lock manager that resides in a single chosen site, say SI. All lock and unlock requests are made at site SI. When a transaction needs to lock a data item, it sends a lock request to SI. The lock manager determines whether a lock can be granted immediately. If the lock can be granted, the lock manager sends a message to that effect to the site at which the lock request was initiated. Otherwise, the request is delayed until it can be granted, at which time a message is sent to the site at which the lock request was initiated. The transaction can read the data item from any one of the sites at which a replica of the data item resides. In the case of a write, all the sites where a replica of the data item resides must be involved in the writing. The scheme has the following advantages. It is simple implementation. This scheme requires 2 messages for handling lock request and 1 message for handling unlock request. It is simple deadlock handling. Since all lock and unlock requests are made at one site, the deadlock handling algorithm discussed earlier can be applied directly. The disadvantages of the scheme are that the site SI becomes a bottleneck since all requests must be processed there. And if the site SI fails, the concurrency control is lost. Either processing must stop or a recovery scheme must be used so that a backup site can take over log management from SI. Distributed log manager. A compromise between the advantages and disadvantages can be achieved through the distributed log manager approach, in which the log manager function is distributed over several sites. Each site maintains a local log manager whose function is to administer the log and unlock requests for those data items that are stored in that site. When a transaction wishes to lock a data item Q that is not replicated and resides at site SI, a message is sent to the log manager at site SI requesting a lock. If a data item Q is locked in an incompatible mode, then the request is delayed until it can be granted. Once it has determined that the lock request can be granted, the log manager sends a message back to the initiator indicating that it has granted the lock request. Advantages are work is distributed and can be made robust to failures. The disadvantage is that deadlock detection is more complicated, so log managers cooperate for deadlock detection in this system. There are several variants of this approach. They are primary copy, majority protocol, biased protocol, and quorum consensus. First, let's see primary copy. When a system uses data replication, we can choose one of the replicas as the primary copy. For each data item Q, the primary copy of Q must reside in precisely one site, which we call a primary site of Q. When a transaction needs to lock a data item Q, it requests a lock at the primary site of Q. As before, the response to the request is delayed until it can be granted. The primary copy enables concurrency control for replicated data to be handled like that for unreplicated data. This similarity allows for a simple implementation. However, if the primary site of Q fails, Q is inaccessible, even though other sites containing a replica may be accessible. Next, let's see the majority protocol. Here, local log manager at each site administers lock and unlock requests for data items stored at that site. When a transaction wishes to lock an unreplicated data item Q residing at site SI, a message is sent to SI's log manager. If Q is locked in an incompatible mode, then the request is delayed until it can be granted. When the lock request can be granted, the log manager sends a message back to the initiator indicating that the lock request has been granted. In case of replicated data, if Q is replicated at n sites, then a lock request message must be sent to more than half of the n sites in which Q is stored. The transaction does not operate on Q until it has obtained a lock on a majority of the replicas of Q. When writing the data item, transaction performs writes on all replicas. Benefits are that it can be used even when some sites are unavailable. Drawbacks: it requires 2 into n by 2 plus 1 messages for handling lock requests and n by 2 plus 1 messages for handling unlock requests. Potential for deadlock even with single item. For example, each of 3 transactions may have locks on 1/3 of the replicas of a data, and it may lead to a potential deadlock. Let's next see biased protocol. The biased protocol is another approach to handling replication. The difference from the majority protocol is that requests for shared locks are given more favorable treatment than requests for exclusive locks. Shared locks: when a transaction needs to lock data from Q, it simply requests a lock on Q from the log manager at one site containing a replica of Q. In case of exclusive locks, when transaction needs to lock data item Q, it requests a lock on Q from the log manager or at all sites containing a replica of Q. Advantages are it imposes less overhead on read operations, while the disadvantage of additional overhead on writes. Now let's see quorum consensus protocol. The quorum consensus protocol is a generalization of the majority protocol. The quorum consensus protocol assigns each site a non-negative weight. It assigns read and write operations on an item X two integers called read quorum QR and write quorum QW that must satisfy the following condition, where S is the total weight of all sites at which X resides. So QR plus QW greater than S and 2 times QW is greater than S. To execute a read operation, enough replicas must be locked and their total weight is at least R. To execute a write operation, enough replicas must be locked so that their total weight is at least W. A benefit of the quorum consensus approach is that it can permit the cost of their read or write locking to be selectively reduced by appropriately defining the read and write quorums. Like the majority protocol, quorum consensus can be extended to work even in the presence of site failures. Now let's see timestamping. The principal idea behind the timestamping scheme is that each transaction is given a unique timestamp that the system uses in deciding the serialization order. Timestamp-based concurrency control protocol can be used in distributed systems. Here, each transaction must be given a unique timestamp. The main problems are how to generate a timestamp in a distributed fashion. Each site generates a unique local timestamp using either a logical counter or the local clock. Global unique timestamp is obtained by concatenating the unique timestamp with the unique identifier. But a site with a slow clock will assign smaller timestamps, but it's still logically correct and serializability is not affected. But there are disadvantages in transactions. To fix these problems, what we need is a mechanism to ensure that local timestamps are generated fairly across the system. So for that, we'll define within each site SI a logical clock, say LCI, which generates the unique local timestamp. It requires that SI advance its logical clock whenever a request is received from a transaction TI with the timestamps X, Y, and X is greater than the current value of LCI. In this case, site SI advances its logical clock to the value X plus 1. Next, let's see distributed query processing. We have seen earlier that there are a variety of methods for computing the answer to a query. We examined several techniques for choosing a strategy for processing a query that minimizes the amount of time that it takes to compute the answer. For centralized systems, the primary criterion for measuring the cost of a particular strategy is the number of disk accesses. In a distributed system, we must take into account several other matters, including the cost of data transmission over the network, the potential gain in performance from having several sites processing parts of the query in parallel. The relative cost of data transfer over the network and data transfer to and from disk varies widely depending on the type of network and on the speed of the disk. Thus, in general, we cannot focus solely on disk cost or on network cost. Rather, we must find a good trade-off between the two. Next, see query transformation. Consider an extremely simple query, such as find all the tuples in the account relation. Since the account relation may be fragmented, replicated, or both, as we saw earlier, if the account relation is replicated, we have a choice of replica to make. If no replicas are fragmented, we choose the replica for which the transmission cost is lowest. However, if a replica is fragmented, the choice is not so easy to make since we need to compute several joins or unions to reconstruct the account relation. In this case, the number of strategies for our simple example may be large. Query optimization by exhaustive enumeration of all alternative strategies may not be practical in such situations. When translating algebraic queries on fragments, it must be possible to construct relation R from its fragments and replace relation R by the expression to construct relation R from its fragments. Consider the horizontal fragmentation of the account relation into account 1 as selection where branch name is equal to hillside from account, and account 2 as selection where branch name is equal to value view from account. Then the query select from account where branch name is equal to hillside becomes a select branch name is equal to hillside on account 1 union account 2, which is optimized into select branch name is equal to hillside on account 1 union select branch name on hillside on account 2. Since account 1 has only tuples pertaining to the hillside branch, we can eliminate the selection operation, apply the definition of account 2 to obtain select branch name is equal to hillside on select branch name is equal to value view of account. This expression is the empty set regardless of the contents of the account relation. Final strategy is for the hillside side to retain account 1 as the result of the query. Next, let's see simple join processing. As we saw earlier, a major decision in the selection of a query processing strategy is choosing a join strategy. Consider the following relational algebra expression: account join depositor join branch. Assume that the three relations are neither replicated nor fragmented, and the account is stored at side S1, depositor at S2, and branch at S3. Let S1 denote the side at which the query was issued. Then the system needs to produce the result at side S1. Among the possible strategies for processing these queries are these. So first, ship copies of all three relations to side S1. Choose a strategy for processing the entire query locally at side S1. Ship a copy of the account relation to side S2 and compute temp as account depositor at S2. And ship temp1 from S2 to S3 and compute temp2 as temp1 branch at S3. Ship the result temp2 to S1. Device strategy is similar to the previous one with the roles of S1, S2 and S3 interchanged. So no one strategy is always the best one. Among the factors that must be considered are the volume of the data being shipped, the cost of transmission a block of data between a pair of sites, and the relative speed of processing at each site. The semi-join strategy. Suppose that we wish to evaluate the expression R1 join R2 where R1 and R2 are stored at sites S1 and S2 respectively. That the schemas of R1 and R2 be capital R1 and capital R2. Suppose that we wish to obtain the results at S1 if there are many tuples of R2 that do not join with any tuple or of R1, then shipping R2 to S1 entails shipping tuples that fail to contribute to the result. We want to remove such tuples before shipping data to S1, particularly if network costs are high. A possible strategy to accomplish all this is: first, compute temp as projection of R1 intersection R2 on R1 at S1. Then ship temp1 from S1 to S2. Compute temp2 as R2 join temp1 at S2. Ship temp2 from S2 to S1. Compute R1 join temp2 at S1. The resulting relation is the same as R1 join R2. This strategy is particularly advantageous when relatively few tuples of R2 contribute to the join. This situation is likely to occur if R1 is the result of a relational algebra expression involving selection. In such a case, temp2 may have significantly fewer tuples than R2. The cost saving of the strategy results from having to ship only temp2 rather than all of R2 to S1. Additional cost is incurred in shipping temp1 to S2. If a sufficiently small fraction of tuples in R2 contribute to the join, the overhead of shipping temp1 will be dominated by the saving of shipping only a fraction of the tuples in R2. This strategy is called a semi-join strategy after the semi-join operator of the relational algebra, denoted as in the figure. The semi-join of R1 with R2, denoted R1 semi-join R2 is projection of R1 over the join of R1 and R2. Thus, R1 semi-join R2 selects those tuples of relation R1 that contributed to R1 join R2. In step 3, temp is equal to R2 semi-join R1. For joins of several relations, this strategy can be extended to a series of semi-join steps. Next is join strategies that exploit parallelism. Consider R1 join R2 join R3 join R4, where relation Ri is stored at site Si. The result must be presented at site S1. R1 is shipped to S2 and R1 join R2 is computed at S2. Simultaneously, R3 is shipped to S4 and R3 join R4 is computed at S4. S2 ships tuples of R1 join R2 to S1 as they produce. S4 ships tuples of R3 join R4 to S1. Once tuples of R1 join R2 and R3 join R4 arrives at S1, R1 join R2 join R3 join R4 is computed in parallel with the computation of R1 join R2 at S2 and the computation of R3 join R4 at S4. Next, let's see heterogeneous distributed databases. Many new database applications require data from a variety of pre-existing databases located in a heterogeneous collection of hardware and software environments. Manipulation of information located in heterogeneous distributed database requires an additional software layer on top of existing database system. This software layer is called a multi-database system. The local database system may employ different logical models and data definition and data manipulation languages, and may differ in their concurrency control and transaction management mechanisms. A multi-database system creates the illusion of a logical database integration without requiring physical database integration. Now let's see the advantages of heterogeneous database systems. Preservation of investment in existing hardware, system software, and applications. Then local autonomy and administrative controls that allows use of special purpose DBMSs. And full integration of heterogeneous systems into homogeneous distributed database is often difficult or impossible, and it's impossible due to these following issues. First one is the technical difficulty. The investment in application program based on existing database system may be huge, and the cost of converting this application may be prohibitive. Organizational difficulties. Even if integration is technically possible, it may not be politically possible. Because the existing database systems belong to different corporations or organizations. In such cases, it is important for a multi-database system to allow the local database systems to retain a high degree of autonomy over the local database and transactions running against the data. For these reasons, multi-database systems offer significant advantages that outweigh their overhead. Next, let's see the unified view of data. Each local database management system may use a different data model. For instance, some may employ the relational model, whereas others may employ older data models such as the network model or the hierarchical model. Since the multi-database system is supposed to provide the illusion of a single integrated database system, the common data model must be used. A commonly used choice is the relational model with SQL as the common query language. Indeed, there are several systems available today that allow SQL queries to a non-relational database management system. Another difficulty is the provision of a common conceptual data. Each local system provides its own conceptual schema. The multi-database system must integrate these separate schemas into one common schema. Schema integration is a complicated task mainly because of the semantic heterogeneity. Schema integration is not simply straightforward translation between data definition languages. The same attribute name may appear in different local databases but with different meanings. The data types used in one system may not be supported by other systems, and translation between types may not be simple, even for identical data types. Problems may arise from the physical representation of data. One system may use 8-bit ASCII, another 16-bit Unicode, and yet another STD. Floating point representations may differ. Integers may be represented in big endian or little endian form. At the semantic level, an integer value for length may be inches in some system and millimeters in another, thus creating an awkward situation in which equality of integers is only an approximate notion. The same name may appear in different languages in different systems. For example, a system based in the United States may refer to the city Cologne, where one in German referred to it as Cologne. Next, let's see query processing. Query processing in a heterogeneous database can be complicated. Some of the issues are: given a query on a global schema, the query may have to be translated into queries on local schemas at each of the sites where the query has to be executed. The query results have to be translated back into the global schema. The task is simplified by writing wrappers for each data source, which provide a view of the local data in the global schema. Wrappers also translate queries on the global schema into queries on the local schema and translate the results back into the global schema. Wrappers can even be used to produce a relational view of non-relational data sources such as web pages, flat files, hierarchical and network databases, and directory systems. Some data sources may provide only limited query capabilities. For instance, they may support selections but not joins. They may even restrict the form of selections, allowing selections only on certain fields. Web data sources with the form interfaces are an example of such data sources. Queries may therefore have to be broken up to be partly performed at the data source and partly at the site issuing the query. In general, more than one site may need to be accessed to answer a given query. Answers retrieved from the sites may have to be processed to remove duplicates. Suppose one site contains a count tuple satisfying the selection balance less than 100, while another contains a count tuple satisfying balance greater than 50. A query on the entire account relation would require access to both sites and removal of duplicate answers resulting from tuples with balance between 50 and 100, which are replicated at both sites. Global query optimization in a heterogeneous database is difficult, since the query execution system may not know what the costs are of alternative query plans at different sites. The usual solution is to rely on only local level optimization and just use heuristics at the global level. Let's say mediator systems. These are systems that integrate multiple heterogeneous data sources by providing an integrated global view and providing query facilities on global view. Unlike full-fledged multi-database system, mediators generally do not bother about transaction processing. The terms mediator and multi-database are sometimes used interchangeably. The term virtual database is also used to refer to mediator or multi-database systems. They provide the appearance of a single database with a global schema, although data exists on multiple sites in local schemas. Now let's see transaction management in multi-databases. A multi-database system supports two types of transactions. First one is a local transaction. These transactions are executed by each local database system outside of the multi-database system's control. Second one is the global transactions. These transactions are executed under the multi-database system's control. We have local autonomy. Local DBMS cannot communicate directly to synchronize global transaction execution, and the multi-database has no control over local transaction execution. But the multi-database system is aware of the fact that local transactions may run at the local sites. Local concurrency control scheme needed to ensure that DBM's schedule is serializable. In case of locking, DBMS must be able to guard against local deadlocks and need additional mechanism to ensure global serializability. Now let's say local versus global serializability. The guarantee of local serializability is not sufficient to ensure global serializability. As an illustration, consider two global transactions T1 and T2, each of which access and updates to data items A and B located at sites S1 and S2 respectively. It is possible to have a situation where at site S1, T2 follows T1, whereas at S2, T1 follows T2, resulting in a non-serializable global schedule. If the local system permits control of locking behavior and all systems follow two-phase locking, the multi-database system can ensure that global transactions lock in a two-phase manner. The log points of conflicting transactions would then define their global serialization order. This concludes Unit 1 of Advanced Database Management Systems. Thank you for listening to my class. We'll see next class with a new module.